Hello, everyone, and welcome to the Friday program of our virtual astronomy days from the North Carolina Museum of Natural Sciences. And my name's Katie, and I'm happy to be the host for this program. I'm really excited about it. And but before we start everything, while we're waiting to make sure everybody gets here, you will probably see on your screen, there's a chat box area, and we have an icebreaker question for you today. And the question is that so many of the planets in our solar system have moons, and they have all these great names. What would you name our moon if we didn't call it Moon? So if you could put some of those answers in the chat box, that would be fun, and we could see, what you guys can come up with. Before we go to, really start, I want to go over a little bit about what the Zoom platform is like. And I know a lot of you have used it, but I'm just going to quickly over it. On the left-hand bottom side, you can see that your camera and your mic will be muted through this whole program. And then for those of you that need or would like to have closed captioning for the program, you'll see down there at the rocket pointing down, you click that CC button, and you're going to click show subtitle. And then you'll see this screen, and you guys can work with it to make sure it's just what you need to have a great program. Okay, and let's see. One more thing is at the top right hand, there are view options, and you want to have, you want to click the side-by-side mode, because we want to make sure our presenter's picture doesn't overlap with his slides, and you can work with that. And this bar in the middle can be moved so that you can get the ratio of the two pictures, just how you need it. And then lastly, of course, we do have the chat box, and we want to hear from you. And we want to know what your questions are about this topic. And we just ask for you to be a good digital citizen and be respectful and on topic with all the things that you ask in that chat box. And that's all the instruction part. And now I'm really happy to be able to introduce our speaker this afternoon. This is Ken Brent, and Ken is a trained NASA Solar System Ambassador. He's also the director of the Robeson Planetarium and Science Center in Lumberton, North Carolina. So our program today, as you know, is Europa Clipper, NASA's next mission to Jupiter. So Ken, I'm gonna give it to you now.
Very well. Good afternoon, everybody. And you may address me as Your Eminence if you wish. No, just kidding. Joking around about that ambassador thing. It's a labor of love. The JPL Solar System Ambassadors Program is a lot of fun, and not always. It also happens to be good for a career in the space sciences. So I need to put this at the bottom. I want to, so it puts out of my way. Okay, maybe not. Does anybody know real quick how to put this, put the Zoom controls on the bottom? No, okay.
So Sean saying drag it.
Drag it, okay, drag it. Okay, let's see. Yeah, it works. Thank you, Sean. Thank you for that update.
Click and drag.
You'd think I would know how to do this by now, right? Okay. So I'm the director of the Robeson Planetarium down here in Lumberton, which is where I'm doing the program from. And we can see the clouds building outside for what happening tonight, hopefully. I run the planetarium down here. We see elementary and middle school kids all over Robeson County and in the southeastern North Carolina region. And we're a partner institution, proud to announce today, with the Moorhead Planetarium in Chapel Hill. So more on that later. That'll be a lot of fun. But today's program, I'm going to also ask you an icebreaker question, literally in this case. What is the most common compound in the universe? Throw it in the chat. Let's see how you do with this one. What's the most common chemical compound in the entire universe? Not element, compound.
Seeing hydrogen.
Okay, that's an element. And yes, hydrogen is the most common element. You're absolutely right, but that's not what I'm asking you. I'm asking for the most common compound in the universe.
H2O, ice.
Very good. Ice or water. Ice is acceptable as long as you say frozen water ice. because as we're going to find out, there's a whole bunch of different kind of ices out there, and water ice is just one of them. Actually, if you tune into one of the other programs about the Dragonfly mission to Titan, or focus in on the New Horizons mission, there's several different kinds of ices on Pluto, to include, of course, water ice, but things like nitrogen glaciers and all kinds of other weird, wonderful stuff that we're not going to talk about today. Because what we've got here, and I'm going to minimize my panel of participants here, this is called the Astronomer's Periodic Table. And I guess I should have put a regular periodic table next to this so you can see what I'm talking about here. So when astronomers talk about the abundance of elements in the universe, they talk about hydrogen and not hydrogen, basically. Because as you can see, for every million atoms of hydrogen, there's a million atoms of hydrogen, of course, but there's 68,000 atoms of helium. You can see where the number breaks down in a hurry. And then we go down to oxygen here. Oxygen comes in at number 3 in the abundance list. So it is no surprise that one of the more common compounds, the most common compound in the universe, is going to be water, because you've got oxygen combining with hydrogen. And both of those two like to play with one another really well, and so they form bonds everywhere, all over the universe. We can see water in the remnants of supernovas even. So water forms pretty much everywhere. And so water is pretty abundant. And of course, as we're looking for things like life outside of the Earth, the thing we want to key in on is that most common compound. Where does it show up, especially in liquid form? Because liquid water is actually in a very narrow temperature range. Okay, so you got all these organic compounds that can form from this. Now, when we're looking at the surface features of these 4 different moons here, you got Titan on the right, Enceladus, Triton, and Europa. Okay, what are we missing from these? I want you to pull up an image of the moon in your head. Okay, preferably something that's slightly magnified so you can see them better. What is the moon covered with? And again, I'm going to ask for someone to read out answers in the chat.
Craters, dust, dirt.
Lots of craters, dirt, dust, everything else. But craters is the major thing I'm pointing out or talking about, because if you look especially at Europa here, Europa does not have craters. It has a few, but nothing like the moon. And so whenever you see a surface, especially a tortured surface like here on Europa or over here on Enceladus, the third one over on the right here, you have to ask yourself, what is going on to remove the record of cratering? Because it's not like places like the Earth and Europa and Enceladus were exempt. They didn't, get the free pass away from the cratering event that happened all over the solar system around 3.8 billion years ago. We call that the late heavy bombardment. And we have evidence of that late heavy bombardment on every object that has a solid surface that is not geologically active. So if your surface is dead, you're more likely to have an extensive record of cratering. Just ask places like Mercury or Callisto, orbiting Jupiter, like Europa is. But our focus in today's program is all about Europa and what we hope to find out in about 5 years, or actually about 10 years when the probe actually arrives at Europa. So the next great mission, one more slide about our icy moons again. So this is the current mission to Jupiter. And this is a beautiful picture of one of the moon's shadows eclipsing parts of Jupiter there as the moon transits or goes in front of the sun relative to the planet. And so Jupiter, if you are lucky and good with an amateur telescope, you can actually image these if you know, and you'll know exactly when to look, because there are tables that are published in places like the Canadian Astronomy Society's observing guide that will tell you when to take out your telescope and look for these what are called shadow transits of the moons of Jupiter across the face of Jupiter as they orbit the planet. This is not something that Galileo saw, but this is something that we saw in later centuries as soon as we started building bigger and bigger telescopes. And of course, the Juno probe took this particular picture, I think 2 years ago, as it was orbiting Jupiter. So we have a probe in orbit around Jupiter right this second called Juno. That's Mrs. Jupiter. for those of you who are familiar with the Roman mythology. So here we go. Hopefully, well, I shouldn't say hopefully anymore. This has been cleared now, and the equipment is being assembled in California and a few other places for the launch of the Europa Clipper. Europa Clipper is designed, as you can see in the picture here, to fly by Europa several times while maintaining a very highly elliptical orbit around Jupiter. So the problem with Jupiter is a radioactive mess. It's a very dirty planet, puts out a lot of different kinds of radiation that will seriously mess up electronics that are not hardwired for it. And so the electronics on a spacecraft like this, like Juno or like Europa Clipper, have to be really hardened to protect them from the radiation. And of course, the other thing you do is you dip you dip your probe into and out of the radiation belts very fast. So your orbit has to be constructed so you don't spend a lot of time in those high radiation areas around Jupiter. And so Miranda, sorry, not Miranda. Sorry, say again.
Katie? There is a question. Is this a real photo? Kim was wondering if this is a real photo.
This is a real photo. That's a really good question. I don't think so. I think this is a really good graphic artist rendering of what Europa would look like to the probe flying over the top of it, gathering data, and with, of course, Jupiter in the background here behind it. So yeah, this is a really nice piece of art right here, actually.
It's pretty, yeah, very pretty.
Beautiful. And that's something to point out. When we talk about space science, we all the time talk about the facts and figures. But sometimes when I come to an image like this, I just kind of shut up and look for a while, because it's really beautiful. Yeah. And, there are all kinds of beautiful images that these telescopes are taken in these places. And you can just, activate the art side of your brain and just go to town with that thing.
Yeah. It makes you imagine things too. It's just really nice. Yeah.
Oh, definitely. You can imagine landing on this icy surface here, one of these broad cracked areas here where you would want to land and send down a lander. We don't have any plans, or NASA doesn't have any firm plans yet to land on Europa, unfortunately, because the real data is in all this orange mush on the surface here. And I call it orange mush. This is another picture of it. This is taken by the Galileo probe back in 2000, and the colors are enhanced to bring out more of the details in the cracks in the ice. So imagine on a cold day this morning, if you were outside or waiting for your car to warm up or whatever, waiting for a bus to go to school or whatever, how many of you shivered?
A lot.
Yeah, a lot of us shivered, getting up, walking outside to start the car to warm it up. It's like, it's cold out here. And you start shivering. Now, shivering is your body's automatic response to cold. What it's doing, well, maybe somebody tell me what it's doing. What is the body doing when it's shivering? Why do you shiver? What's the purpose of that?
Several people are shivering right now.
Yeah, it's kind of cold in here too. But
one answer is to warm up.
Yeah, exactly. But how? What mechanism is used here to warm you up? What force is being applied across the tissues of your muscles to warm you up?
I'm seeing muscles.
Yeah, muscles. What are the muscles? What are my arms doing right now? They're rubbing back and forth against each other, right?
Yeah.
Guess where it's warmest on my body right now? Right in between these two arms. Because friction makes things warm up. So imagine my arms now as muscle fibers sliding back across against each other and doing it quickly, of course, and that creates heat. Now, replace muscle fibers with sheets of ice and replace the action of contracting the muscles with the push and pull of gravity. Remember, Europa orbits the biggest planet in the solar system, and its orbit is slightly elliptical, so sometimes the force of gravity is greater than other times. The other thing happening here is you've got three other big moons called the Galilean moons, Io, Callisto, and Ganymede, that also exert their gravitational influence on Europa. So Europa's surface gets pulled and tugged back and forth and back and forth. Now, on Io, it's a different situation because the body of the moon is made out of of Io is made out of a lot of sulfur compounds. And with that friction, because it's even closer to Jupiter, you actually melt the sulfur compounds down in the silicates and form volcanoes. And so some of the most active volcanoes in the solar system are on Io. But Europa is the second moon out from Jupiter, going out from Jupiter. You got Io, Europa, Ganymede, and Callisto. Europa's second one out. So the force of gravity is not as strong from Jupiter, but it is every bit as strong from its neighbors, from Io, from Ganymede, mostly, that provide most of the gravitational flux, the back and forth, that causes the ice to actually break here. And underneath the ice, because of that friction again, and because of what they think is maybe the heating of the solid part of Europa underneath the ocean by this friction, you have a lot of hot spots and you have the melted ice. And melted ice, of course, is what you swim in. So the big question is, and the question we're not going to be able to answer yet, I don't think, is what is swimming in the waters of Europa? That's a big question.
So does the vein light, well, that was a comment from the audience, is it looks like veins.
It does look like veins.
Is that where the water is? Is that what you're saying?
But here's what happens. The ice cracks. And you got a liquid body of water underneath, and the water forces itself up through those cracks. Because don't forget, the Europa also has gravity, which means its gravity is pulling down on that outer shell of ice all the time. So it's creating some pressure on the surface of the water. Now, when the crack opens up, the water leaks out. In the same way, if you bust a pipe with a wrench or something, water will leak out in the same way. If you crack the pipe, or if you crack, say, a PVC pipe, water comes out. And the same thing happens here, except the water out here, as soon as it hits the surface, it freezes, basically. It's right away kind of freezing. And the water that comes out of these trenches here is not clear. Look at the color here. We're looking at oranges and reds and things like that. And we know from spectroscopy that those are organic compounds. And there's quite a slew of different organic compounds on the surface. I mean, are those actually bodies of some sort of plankton that have been forced out on Io's surface and frozen? I mean, we don't know. We just don't have the detailed images to be able to pull that down. So that's one of the big questions that the Europa Clipper might answer is what is the stuff made out of? I mean, and if it gets close enough, can it actually image bodies? If, say, whale bodies get thrown out on the ice, we don't know. You never know what you're going to find when you look at something like this.
Henry says he plans to figure it out when he grows up.
Oh, please do, Henry. We need all the help we can get, man. I'm serious.
That's very cool.
This is one reason why I love teaching about space science, because we are not done. If you know what I'm saying. Because as soon as Europa Clipper flies over and gets they're going to be close enough where they're going to be within 100 kilometers or so of the surface, maybe even closer. I forget the actual depth, but there's some that are really close to the surface. They're going to be flying by here with the Clipper. And all that new data, what's the first thing that's going to happen? You're going to get some data. And then what does the data mean? How did that happen? What are the causes of this? Why do we end up with perchlorate up here? We don't, all kinds of questions we don't even have yet because we don't have enough information. Right. So astronomy never dies. It's one of those sciences. It's not like somebody wrote the book, Mark Twain is always going to have written Huckleberry Finn. Okay, that's a done deal. It's done over, he's long dead. So we're never going to get Huck Finn 2, the sequel. No, not going to happen unless somebody takes some serious liberties with Twain. But here, astronomy is a constantly evolving science. When I started teaching high school, one of the first things I told my students was, we have planets in our solar system. Why do these other stars not have planets? How does that work? My guess, we're going to find planets around those other stars. It will take better technology, better imaging systems, and better hardware, and the software to detect what's on the hardware. And lo and behold, 5 years later, bang, planets. And now we know about over 5,000 confirmed planets, and we're not even getting started yet. So you want to talk about an expanding field where there's always going to be a career for you waiting if you want it, is astronomy. Because we're still going to be learning stuff long after I'm dead. So let's move on. Oops, there we go. Go. All right, I should be getting a video here. Let me know if you're not hearing and seeing this when I hit the play button.
Right.
Whoops, I hit the wrong button. Okay, let's hit that button.
Hubble has found even more evidence of water vapor plumes on
Good.
the ocean world Europa. Last September, we announced that the Hubble Space Telescope had taken multiple images of what could be water vapor plumes on Jupiter's moon Europa, an icy world that's thought to have a subsurface global ocean of water. That same team of astronomers has now taken additional ultraviolet images of probable plumes on this icy moon. While these plumes seem intermittent, they appear to have repeated in the same location. Pieces of the puzzle of what's going on with Europa are continuing to come together. When the Galileo spacecraft was orbiting Jupiter in the late 90s and early 2000s, it gathered data to build a thermal map of Europa, and it appears the water vapor plumes Hubble is observing correspond with a relatively warm region on Europa's southern surface about 200 miles across. This thermal anomaly the Galileo spacecraft observed suggested geologic activity was happening in this location, a conclusion now further supported by Hubble's recent observations of water vapor plumes. This phenomenon may be similar to what the Cassini spacecraft has seen at Saturn's moon Enceladus, where there are also water vapor plumes associated with warm regions on the moon's surface. The warm spot on Europa has a couple possible explanations. Perhaps this location is warmed by liquid water a mile or so under the surface, pushing up through the cracks in the ice. Or perhaps the fine mist that's falling from the water vapor plume changes the structure of the surface ice grains, allowing them to retain heat longer than their surrounding landscape. Now that Hubble has shown Europa probably has water vapor plumes associated with warm spots on its surface, this information will be used for planning NASA's upcoming Europa Clipper mission. Europa Clipper will be able to take up-close observations of these probable plumes Hubble identified, and will be equipped with instruments that can detect any additional warm spots and water vapor plumes. This will provide insight into Europa's chemistry, geology, and potential conditions for harboring alien life.
Okay. Good job with the sharing there. Okay, so let me go ahead and pull up another video for you. Nope. Oh no.
Well,
Okay, give me 1 second. I pulled up the wrong video earlier, so I need to open up a different.
there was a question from Jasper.
Go ahead. This is a good time.
Bruie, B-R-U-I-E, might explore Europa.
Rui. Who launched this
Jasper.
particular?
Jasper, can you tell us a little bit more about Bruie? Or maybe I'm not saying it right. It's B-R-U-I-E. Let's see, what else? While he's figuring, here he goes. JPL was the answer to that.
Oh, okay. All right. Well, that may be a mission in the planning stages I don't know about yet. That's entirely possible.
Okay.
So let's get rid of this.
Here it goes. Bruie, buoyant rover for under ice exploration.
Oh, very nice. Yeah, if we can pull that off, that'd be wonderful.
Wouldn't that be cool?
Yeah, it'd be
Wow.
very nice. Yep.
There
All
was
right.
another question, whether Clipper will orbit. Hold on, it went up too fast. If Clipper's going to orbit, what's the question? Here, well, I'll find it. Whether it's going to orbit Europa. I think it's what the rest of the question.
No, it's not going to orbit Europa per se. It's going to orbit Jupiter with a focus on Europa. So the timing of the orbit will time with Europa going around Jupiter. So my guess is there's a point where Europa comes out of the radiation bath, and that's when the Clipper is going to interact with it and do flybys and things. So the mission is timed. I think there's a total of 22 flybys of Europa it's going to take, varying depths. And of course, the closer you get, the better your images are, the more resolution you can tease out of your cameras. The other thing to notice is that these probes are being powered, both Europa Clipper and Juno are powered by the sun. And if you
Huh.
think about that for a second, that doesn't really make a whole lot of sense because Jupiter
Very
is
far
5
away.
astronomical units away from the sun. It's pretty
Yeah.
far away. So the intensity of the solar radiation is a lot less out there. It's like 1/25th what we get here on Earth, roughly. So, so the radiation would be the solar light that you're actually going to use to power your spacecraft is a lot dimmer, and
Yeah.
yet they're able to do it. So that's pretty cool.
Yeah.
All right, so here we go with the next video. This is about Europa and the ocean world, and it's narrated by one of my favorite JPL scientists, Dr. Papandreou. Are you hearing that okay?
Uh-huh.
The
Yeah.
search for life beyond Earth begins with understanding life on our home planet. And that story, the story of life on Earth, may have begun in our oceans. And that's because, of course, if we've learned anything about life on Earth, it's that where you find the liquid water, you generally find life. So what if I told you that there is an ocean out there beyond Earth? An ocean in our solar system that has been in existence for billions of years. It's an ocean that is perhaps 10 times as deep as Earth's ocean. It's an ocean that is global and may contain 2 to 3 times the volume of all the liquid water on Earth. It's an ocean that exists beneath the icy shell of Jupiter's moon, Europa. So how do we think we know that Europa's ocean exists? Well, it's a combination of using telescopes on the ground and having spacecraft that have flown by Europa and collected data about the surface, about the interior structure, and about the magnetic field around Europa. And the combination of those data sets leads us to a high degree of confidence that this global liquid water H2O ocean is there today, and it's been there for much of the history of the solar system. We used to think that in order for a world to be habitable, you had to be at just the right distance from the sun or whatever your star was, such that you could have a liquid water ocean on the surface. Now, along with liquid water, life as we know it needs 2 other keystones. The first is the building blocks for life, the stuff you find in rocks. And the second is some form of energy to help power life. And here's where Europa is a real game changer. It is far, far out from the sun, and yet it's got this liquid water ocean. And the reason that Europa has liquid water is because it's orbiting Jupiter, and the tidal tug and pull causes Europa to flex up and down, and all of that tidal energy turns into mechanical energy, which turns into friction and heat that helps maintain this liquid water ocean beneath an icy shell. Along with helping maintain liquid water, we think that tidal energy may also allow that ocean to interact with rocks on Europa's seafloor. And it may even give rise to things like hydrothermal vents, which could help provide not just the building blocks for life, but also the energy for life. The question of whether or not life exists beyond Earth, the question of whether or not biology works beyond our home planet, is one of humanity's oldest and yet unanswered questions. And for the first time in the history of humanity, we have the tools and technology and capability to potentially answer this question. And we know where to go to find it. Jupiter's ocean world, Europa.
Now I'm going to stop it there so we can use this backdrop here to answer questions with any other questions you all have about Europa or her missions upcoming.
There was a question, actually, how big is your Europa?
Europa is roughly about 2,000 miles in diameter, or put it another way, about the same diameter as our moon. So
Okay.
Europa would be about 1/4 the size of Earth. And so the gravity being exerted by Europa on whatever's swimming is a lot less than the gravity that's exerted upon the objects or things swimming in our oceans here on Earth, because Earth is a lot more massive. So it'd be roughly, I'm going to guess, maybe 1/6 or 1/7 what you would feel swimming around just underneath the surface here on Earth. When you start to go deeper, you got other forces to consider.
Right. Stephen said that the radiation from Jupiter, wait a minute, the radiation from Jupiter does not penetrate through the ice. Is that correct?
I'm pretty sure most of it won't, yeah, because ice is a pretty effective shield. It's almost as good as our atmosphere in terms of shielding out things like ultraviolet rays and things like that. But there are some particles that are going to get released, very high energy particles, that a little thing like a block of ice is going to stop it. But I don't think the radiation is significant enough to affect or mitigate the formation of life.
So there is also, Kim has a question, how can a thing live without oxygen?
Well, that's really good. There's a lot of things that live without oxygen. As a matter of fact, last time, anytime you're walking around in the yard and somebody stupid left a board out there with a nail in it, right? And you step on the nail, okay, you end up with a puncture wound. Now, what's the first thing somebody pours into that puncture wound when they start to treat you?
Peroxide?
Peroxide, right? And peroxide is well named, H2O2. So when you hit a surface with hydrogen peroxide, oxygen gas gets liberated. And the reason you're doing it, you want to kill the bacteria that were on that nail that are anaerobic, that don't need oxygen. There's a whole community of organisms out there that are anaerobic. Yeast is one example of an organism that can do either. It can either go anaerobic or it can go aerobic, using oxygen or not, depending on its environment. So there are many things that don't require oxygen. What you have to have is some sort of mediating molecule to do energy reactions with. And there are lots of models out there in the astrobio community that show other substrates. Sulfur is another possible substrate for energy reactions to be mitigated or to be what I call stair-stepped. So instead of, when you burn a piece of paper, you're converting the sugar in the form of cellulose in the paper to water vapor and carbon dioxide if you burn it completely. Whereas when you take a molecule of sugar inside your cells and your cells break it down and get the energy coaxed out of the molecules of the sugar molecule, it's a long process where there's a little bit of energy released at every step that the cell can use. And so that stair step is the same exact combustion reaction that's happening when you light up a piece of paper, but it's going a lot more graduated or gradual. And so the cell can tease the energy out of the molecule without killing itself, basically. But there's lots of different chemicals out there that can replace oxygen in that kind of reaction. So oxygen is not a necessity for life as we know it.
Yeah, I think a lot of people are thinking about larger animals and fish and that sort of thing.
Oh yeah, well in that case, you have to have something a pretty good oxidizer in your chemical makeup somewhere. So we may find a totally alien chemistry going on if we find living things in Europa. The biochemistry of these things may be radically different than what we do here on Earth. So again, there's so many things we don't know yet.
Yeah, it's pretty cool. So Stephen said, so life under Europa could be carbon-based, but otherwise not use sugar or proteins or DNA, just some other structures depending on evolution. Do you think that to agree? Yeah.
Well, I don't know. I mean, it may be that evolution follows the same paths no matter where you go because of what they call chemical expediency. It's the easiest chemical reaction, so you need to do it with these chemicals, basically. Or it can be much more diverse than we can even imagine. The problem with living on Earth and trying to learn about biology off-world is that we walk in the room with a whole bunch of prejudices in our heads about what life ought to look like and what life ought to do. The life under the surface of Europa may be completely radically different from anything we can even imagine. I mean, we don't know. And that's the beauty of this. We don't know, and we need to find out. So the young man who said earlier, I need to grow up and find this out, you're exactly right. Keep studying, man.
That's cool.
Study hard.
So let's see. Kianan has asked, oops, the question just went up, about eclipses.
Mm-hmm.
Let me get up one more. Okay. How often, if it was possible to live on Jupiter, how often would you see an eclipse?
I don't know. It would take some figuring, but you could start with the tables, the observing tables that tell you how often moons transit Jupiter in a direct line with the sun, because you got to have three things happening. You know, you have to be on the right part of Jupiter, and Jupiter is a pretty big place. So say you're floating around in a gondola, you know, on a balloon floating in the cloud tops of Jupiter, and your pressure controlled gondola, if you're flying around there, you would see an eclipse. You had the potential to see them pretty often. The question is, does the moon cross in a particular place on the planet where it always eclipses the same place, or does it cross in different places, interact with the planet? I don't know. So that's an excellent question to chase down and do for homework.
That's fun. So how are these moons going around Jupiter? Are they all different sorts of orbits?
They all go. The rule is, in general, an object rotates counterclockwise and orbits counterclockwise, whether it's a moon or a planet in our solar system anyway. Everybody moves counterclockwise, with one, of course, there has to be an exception, right? Venus is that exception. Venus rotates clockwise on its axis. And a lot of people think it's because of a major impact just slowed it the heck down and took out its relic. What you're seeing when you're seeing the planets spin in orbit, or the moon spin in orbit, you're seeing the relic motion from the actual formation of the solar system itself. From the coalescing of a big dust cloud, everybody spinning around, forming smaller clouds. And so Newton's first law says an object's going to keep going in the same direction it's been going unless you change the forces involved somehow. You exert a different force on it. So with the moon going around Jupiter, it's mostly going through empty space. So there's not a whole lot to slow it down or speed it up, for that matter. And the moons enter into this balance where their forward motion is offset by the amount of gravity pulling down on them. So yeah, that was a long-winded way of saying yes. I'll go the same way.
That's what astronomers do, right?
Sorry.
So Jasper's saying, if life started on Europa, could it get to Ganymede or other moons of Jupiter, or vice versa?
Well, how big an impactor do you want to throw at it? That's the short question. There's a theory out there called panspermia, and I'll put that in the chat so you guys can look it up later. Where's my chat button? There it is right there. All right. So I'm going to put, somehow I got it. Oh, there we go. Okay, the theory is called panspermia. Panspermia. There. Okay. And the theory suggests that life spreads by way of impact cratering. So, for example, meteors from Mars can make it to Earth because a rock will hit Mars, or a comet will hit Mars, blow off pieces of its surface. Most of those pieces go randomly off into space, but a couple of them will get captured by Earth's gravity and then get pulled down to Earth as meteorites. And one of the places you find them best is Antarctica, because basically you got a white plain on top of which are dark rocks. So they're very easy to spot. You're driving across in a snowmobile or whatever, and you see a dark spot on the ice. It's one of two things, but hopefully it's a rock. And if it's a rock, it probably came from out there, because there aren't a whole lot of rock formations around these big plains of ice that are down in Antarctica. Is one good place to look for meteorites.
That's really interesting. I never knew that.
So if you hit Europa with a big enough impactor that could splash water out into space, and the water freezes, and the water then lands on, so the ice then lands on Ganymede, and something happens to melt the ice, well, then all those cool little spores or whatever it reproduces with get unleashed into Ganymede's ocean, and you end up with life on Ganymede. So that's one possible way to explain the spread of life throughout the universe. or just for us even.
Let's see. Stephen said going uphill to Ganymede might be hard, but then orbits can gain speed in weird ways. So maybe, but most would go downhill to Jupiter.
Yeah, exactly. He's right.
Well.
Yeah. I mean, if we talk about, Stephen's talking about gravity the way a lot of physicists talk about it in terms of wells, like climbing up out of a well to escape the, you don't have to worry a whole lot about escaping Europa. The gravity is pretty low there. So you hit it with a rock, most pieces fly off, and a few of them will fall back down on Europa. Most of the ice is going to fly off. And like you say, he's exactly right. Most of that is going to end up hitting Jupiter because Jupiter is the major gravity force out there. But if the object goes flying away from Jupiter and Ganymede just happens to intersect with it, there you go. So it's not, I mean, I wouldn't suspect it to be very common, but it definitely does happen, I'm sure.
So the question is, what data will Europa Clipper collect that could help us know there is life in the ocean?
Well, the one thing it's going to do, they have spectrometers aboard, the same kind of spectrometers that were aboard Cassini, the orbiter that went around Saturn for like 15 years. Cassini actually was able to sample the plumes coming up from Enceladus, the ice plumes. And Cassini found things like 4-carbon sugars, the sugar ribose. Maybe you've heard of that. That's the oxyribonucleic acid or ribonucleic acid. Well, the ribo is a prefix for ribose, the 4-carbon sugar. And so they found that in the gas cloud coming off of, or the ice and gas coming off of Enceladus. So they're going to do the same thing with the plumes on Europa. They're going to interrogate them with spectrometers or I think a chromatograph to actually figure out what elements are in the plume in addition to water. So yeah, and there's a lot of other instruments too. They're going to use a ground penetrating radar to try and figure out how far down do you have to go before you hit water, because that's definitely going to be important for a lander. If you can land in a spot where you only have to drill through 100 feet of ice, you want to go there versus the spot where you got to drill down through 2 miles of ice.
That's so funny because Marcel just asked that. Marcel just asked, he says, how thick is the ice? Miles? So.
It depends on who you ask right now, honestly. A lot of planetary scientists are now going with the kilometer or less thickness in the places where you see the dark splotches or the cracks. Those are going to be places where the ice isn't as thick because after all, when it froze over and formed again, there are lots of, when you saw that surface artist impression of Europa, there's lots of hills and valleys caused by these crevasses. And I'm going to imagine some of those crevasses are really deep, Grand Canyon kind of deep. But again, I don't know. I'm not too familiar with the surface features of Europa.
So how long is a day on Europa? Do you know that?
I don't know. I know that its orbital period is around 18 days, I think. That's the time it takes to go around Jupiter once. But the day is going to be, I don't know. You got me. You have stumped the chump, as they used to say at Car Talk.
Coming at you fast and furious now. Let's see. Would the Clipper have an ending like Cassini when it ran out of fuel? Or
exactly. Exactly. And that's exactly what they're going to do with Europa too. So the person who asked the question about Cassini, you remember that Cassini was actually directed to fly into the cloud tops of Saturn and burn up. And that was very much a purpose pitch. That was designed all the way. When the Clipper runs out of fuel and can no longer navigate, one of the last navigation commands will be descend into the cloud tops of Jupiter and burn up. Because the last thing you want to do is have your craft crash and contaminate the surface of whatever it crashes on. If it burns up, you're going to sterilize the contents and everything inside it, because going down through Jupiter's atmosphere, there will be nothing left when it gets all the way to the bottom, wherever that is.
How big is that spacecraft?
How big is the spacecraft? It's about the size of a school bus. The business part of the spacecraft would be like where all the instruments and the antennas and everything are. Most of that is going to be within where the driver and the bus door would be in a school bus. And then the wings, the solar panels, will be about the size of a school bus going off on each side.
Oh, wow.
Pretty big. And about 6 feet tall, I think. So pretty big. It would fill up an elementary school cafeteria pretty nicely.
That's good. Good image there.
Yeah.
Let's see. I'm trying to see if there are any other questions.
Okay.
I think that we've come to the end of the questions. Let me keep
Okay. All right.
data. Yeah.
Well,
that was really fun.
Thank you.
I learned some new things there. That was really cool.
That is
yeah. So let's see. So, well, thank you very much. That was a great program, and thank all of you guys for being such wonderful. Oh wait, somebody say wait.
What?
They're just they're wanting to see the different websites that are being posted. That's all. They didn't want it to go away. All right. Anyway,
okay. That's fair.
This audience is really great. I thank you guys for coming. You're really into it. It's really fun.
I wonder if this is the same Sean that asked me yesterday if duct tape works on Mars. That was an awesome question. I'm still talking to people about that one. That was great, Sean. Because the answer is duct tape works everywhere, man.
It is.
Unless you're in the rain. It doesn't work too well in the rain, but duct tape works everywhere. But Sean asked how many moons are on Jupiter and around Jupiter. And I said, I'm going to tell you at least 79 and counting.
Wow.
Because every time they took more looks, like Pioneer data from the mid 70s, when it flew by Jupiter, it took pictures a lot of people didn't really look at because they were looking at the interesting ones with moons in them. But, it's very possible that in that archive data, you're going to see the paths of smaller moons that weren't detected the first time.
Yeah.
Or in any of the other flyby missions of Jupiter or Hubble images even. Yeah.
That is very cool. Yeah, it was the same, Sean. I want to make sure before we leave that we say thank you to our sponsors for these programs. And one is the North Carolina Space Grant, and the other is Pepsi Company. So many thanks to them for really supporting us. And also the Raleigh Astronomy Club has been partnering with us to get you guys all together to do these wonderful presentations. It's really fun. Let me see what other people are saying. Oh, they're still guessing the number of moons.
I don't know. I can't tell you the actual answer. I'm sorry.
That's really funny.
Because it depends. Last week it was 78. Who knows?
And we also want to thank our members, our Friends of the Museum members. I'm going to pull up a slide because for our members, I have to share. I have to figure out how to do that. Share screen. Hold on. It'll be a second. We have an Astronomy Day t-shirt that we have designed for this year. I'll get it up here in a second. There it is. Share. All right. And our members will get a discount on this, on t-shirts and a hoodie too. You can order it from our museum store or get it at the museum store when you go down there. And those are my announcement type things. I just want to say how great this was. I really enjoyed it. This is my first one. So yeah, it was very fun, Ken. And thanks everybody for your questions. So I do have to make sure to tell you, we're not up. The astronomy days that keep going. And it's about 10 minutes. There's the next program is going to start. And also we have programs on Saturday and Sunday. So be sure to keep looking at our website and seeing what you might want to see next. We also have recorded all of these programs. So if you miss one, you have to miss it, you can go back and see it, the recording of it. So wonderful. Thanks so much.
Thank you very much, you all. We were a great audience. It was a lot of fun. I love doing these every year with you guys. The museum, you guys are wonderful to work with. So cool. Thank you.
That's great.
And I hope I win the trivia tomorrow.
Yeah, I guess. There you go.